Good afternoon, my name is Fabio Ducati, and in this presentation we will introduce my research activity on the design of radio frequency integrated circuit for sensor and multimedia application. Here is the list of the circuits that I have designed during my PhD. The first one is a broadband TV tuner for cable television that I have designed during my internship in Philips on the first year, now NXP. Then the aggregate control system, also this circuit has been designed here in Modena, but in collaboration with NXP. Then a 9 GHz radiometric system for fire detection sensor. At the end, two new kind of circuit, a programmable input sensitivity Prescaler, and an high linearity Q-band CMOS LNA that has been designed in collaboration with the Polytechnics of Nice and with Entropic, that is a USA company that has a research lab in Sofia Antipolis, where I spent 3 months as an internship. Let's start with a broadband TV tuner for cable television. Here is reported the function, the block of the front end. This is represent a new architecture because this receiver is a multi-channel capability. It means that it's able to receive more channels at the same time. So here in red is the RF front end. This is the one I have designed, and the architecture is present a radio frequency analog to data converter. After that, we have the signal that we have received is digital, so we can process with DSP or what else. More in detail, here is represented the architecture of the RF front end, where there is a 2-stage of amplification, a low noise amplifier and a voltage gain amplifier. More in detail, we have here is reported the front end block diagram. Here is the 2 amplification stage with the resistor network that implement the variable gain. We need a variable gain because at the output of the system we need of a constant output power because we have to drive the analog to data converter. While at the input power is not constant. It depends on the number of the carrier that we receive and also of the kind of cable and so on. So we can choose the gain, changing this resistance that are drive with in a digital way with some bit. Here is reported more in detail the schematic of each block. We can see that the LNA and the VGA are basically composed like a chain of inverted stages, and we have here and here the resistance network with the switching transistor that switch on or switch off the resistance in a digital way. Here is the new kind of linearization circuit that has been introduced in order to improve the linearity of this front end. Here is the same block, and here is in detail the gain configuration that we have chosen and designed for this application. It was not so easy because from the gain composition of the amplifier it depends linearity, instability, so phase margin, in terms of phase margin, noise of this system. So we need to find a trade-off between all these parameters. So we can see that in violet we have the VGA gain step, and in blue the LNA gain step. The sum of the two represent the gain of the system that is linear, and we can see that when we have high voltage at the input we have less gain, and we have low power input we have more gain. This is a representation of the simulation of the principle of behavior of this linearization circuit. We can, in the first approximation, assume that the voltage gain of an inverter, that is the core of the amplifier, is equal to the product between the transconductance, GNM, and the output resistance, R out. So we can linearize or this term, R out, or GNM. The way to linearize GNM is usually a narrow band solution. It is not possible to apply in this case because this amplifier has to present a wideband around 1 GHz. So I decided to design a circuit able to linearize the R out. So we can see that this is plotted the product between GCONM and the route without an initiation circuit of an inverter, and we can see that is not flat, so it's not so linear, and with the linearization circuit that now is really, really flat. The drawback is that we lost a bit of gain, but this simulation is in an open circuit simulation. So when we close the circuit in a feedback, this drop is not so evident, and the gain is almost the same. Here is the layout of the chip. We can see the LNA, the VGA, the output circuit for linearization, and the shift register that has been used for setting the gain of the amplifier. After this, the collaboration with NXP is continued in Modena and in the design of a backgate control system, where I studied the possibility, the advantages and the drawback of this solution. This solution is a patent from NXP. And the idea is that if we have an amplifier, we can boost its GCONM, stabilize its DC performance in order to increase power rejection with a 2 voltage backgate voltage generator. This is the circuit that we have used for test. We have an amplifier, just an inverter, that is more or less the core of the one that I've designed there, with a resistor and feedback. And here is the backgate generator that is reported here, more in detail, the block. It's constituted by a current source that to be stable in temperature and bias variation, and a differential amplifier. This feedback circuit has to provide a voltage able to maintain this current constant. So if I mirror this voltage on the NMOS transistor inside the LNA, the same is for the PMOS, I can have the same constant current also in this section, so in the amplification stage. Here is the simulation, and you can see that the current that flows inside through the inverter is almost constant. This is a S-shaped, but if you look at the value, we see that if the temperature varies from minus 40 degrees to 140, the current presents a variation of only 0.4 milliampere. Sorry. And so it's really good performances. Here is the current also, that flows through the inverter, so through the amplification, with a variation of polarization of bias voltage. And we see that it's flat between 1.6 to 1.24 voltage. The nominal voltage is 1.2. And before the voltage headroom is not enough to polarize all the circuit, so it is switched off. And if we go too higher, the transistor goes in lights up condition, so it stops to work. So this is the limitation of this idea in this application. After that, during my PhD, I designed a 9 GHz remit system for fire detection sensor, and this work was implemented during my first and second year of PhD. We start with a short physical description. We can say that the outer surface generates a black body radiation that depends on temperature, for example, if you look at the sun, the fire, or the earth, and frequency. So, changing the temperature and the frequency, we have different emission. We are, for our application, interested in this area for radio frequency and microwave wavelength, because in this area we have an emission that is able to go through the smoke and the rain, so we can see if there is a fire, also when it's not possible to see. So also if it's not visible. And this means, but the drawback is that the emission in this area is really low, so we need a high gain antenna and a low noise front end and amplify receiver signal. Here's the design of the system block. When there is an antenna, the amplification stage, the mixer, the synthesizer, and then when we down conversion the signal from RF to baseband, we have a baseband system that is not studied from us. We have designed the LNA, the synthesizer that is a PLL, and the mixer of down conversion. Here is reported the specification that has for the system, the gain that has to be more than 20 dB, and the noise figure, especially for the LNA, that has to be less than 2 dB. Here is the picture of the chip. You can see the PLL, because you can see that we are a homogeneous architecture. We have the LNA, the mixer of down conversion, and the PLL with the double that work as a local oscillator. We have the PLL with the double. Here is the mixer, and here is the LNA. And here you can see the test on the chip that show that we have a 180 megahertz of output bandwidth from 10 to 120 output frequency. And we can see that we are able to detect a power input of around minus 85 dBm. So it is very sensible, and it looks to work really good, as expected. After that, during my last year, I designed a programmable input sensitivity Prescaler. Usually, Prescaler is a frequency divider that presents a V-shaped narrow band sensibility input. So, usually, a Prescaler has been designed to work for a certain input frequency. The idea is to, in this case, to design a Prescaler that can work with two different input frequencies. Here is the Prescaler architecture. Is a flip-flop chain of division, starting from a high-frequency division block to the low-frequency division block with some buffer stages to clean the signal and make it more squared. And here is the core of the new idea. We have designed a bandgap reference able to generate two different voltage that has to be constant under temperature and bias variation, and a multiplexer that can be choose the one of the two voltage generated. So with a bit we can select one on the other voltage. So we change the polarization of these first stages, and so we change the sensibility, the input sensibility of the system. We can see that this is the classical V-shaped input sensitivity of a Prescaler, and we can see that if we polarize the first stage with 760 millivolt, we have the maximum sensitivity around 7 to 5 gigahertz. If you change this, if we switch to with the multiplexer to 830 millivolt, the maximum input sensibility is now at 5 gigahertz with the same input power. So we have shifting frequency, the input sensitivity of the Prescaler. Here is reported just in a time domain as it works. So we have the high frequency, and then we have less frequency goes to the baseband frequency due to the chain division. This is the layout of the chip. We can see the voltage reference at the beginning, and then the chain division that is implemented here in the core. At the end of my PhD, I designed an high linearity Q-band CMOS LNA for satellite application, collaboration with Polytechnic of Nice and with Entropic. Here is the basic schematic of the amplifier. You can see M1, that is the common gate input transistor, M2, that is the common source output transistor, and then we have two feed-forward, M3, that is the feed-forward transistor that is used for improve the linearity of the system. Then we have two feedback network for improve the bandwidth and the linearity of the system. Here is M4, M5 with these two resistors has been designed to polarize the output stage. Here is we have also the LS1, the inductor of input for the input matching, LD2 that is for output matching, LD1 that is the inductive lobe of the first amplification stage. Here I reported the simulation result. We can see that S21 in a scattering parameter is more than 10 dB, around 12 dB at 15 gigahertz. S11 represents the input matching of the system. That is really good because it's less than 20 dB, minus 20 dB at 15 gigahertz. Then we have the noise that is less than 4.5 dB, and is the key factor that ensures us that the circuit doesn't oscillate. Here is reported the linearity of the system in terms of 1 dB compression point, and that is around minus 4.4 dB. That is really, really good. Also in literature, nobody has done better. Here are the test results of the system. In this case, we see that S11 is more or less the same that we have simulated, but is not at 15 gigahertz, but is at 14. Is detuned as the other simulation due to the fact that we have not an extraction tools. So we underestimate the parasitic effect, and at 50 gigahertz is quite sensible, the system to parasitic effect. Here is also the S21, that is the gain of the system, that is less than the one simulated, is not around 10, 12, but is around 6, 7, and is not at 50 or 40, but is centered around 12. This is because the inductor model that we have used, we use a ST model of library, and ST make its model wrong. After this result, we make an electromagnetic simulation of the inductor of ST, and we extract a model, and we have see that the model of ST were wrong. So in the future, we have to extract by ourselves the model of the inductor. It is the 1 dB compression point, so the linearity that is either the one simulated. This is because the gain is goes down. Yes, the last two scattering parameter here is S21, that is the highlight that output is well isolated from the input, and the S22 that show that also output matching is good. Here is the picture of the system. Here is the core of the LNA. Here is the pad ring that is put between the inductor and the core in order to minimize as much as possible the parasitic effect, and here is the inductor. It is my publication that I've done during my PhD. I have finished. If there is any question.
Question? I have a question. I don't know if I missed that, but I saw the simulation concerning the noise of your LNA, but I didn't see the test result.
After see that the gain went down, we are seeing that it's around 10 dB, not around 4.
I see.
Because the gain is dropped down, so now we have not
yes. Okay. Thank you.